Find inverse Z transform of the following using partial fraction expansion. So you have been given a Z transform and you have been asked to find Xn, that is come back to time domain by applying inverse Z transform using partial fraction expansion method. And the very important thing is that when we are obtaining a discrete time domain signal, we have to maintain the ROC for the given equation. Okay, so this ROC plays very important role while deciding the discrete time domain signal. So this ROC decides whether your discrete time domain signal is right-handed, or it is a left-handed signal, or it is a two-sided signal. Okay, so let us start with simplifying the given system. So very first thing that we'll do is we'll eliminate the negative powers of Z. We'll make the given system entirely with a positive power of Z. So we'll eliminate all the negative powers of Z. So for that, how to do that is we have to take the highest power common from the numerator and also from the denominator. So what is the highest power in the numerator is Z raised to minus 2. So we have taken Z raised to minus 2 common here. What leaves inside is Z square, right? This 1 becomes Z square if I take Z raised to minus 2 common. Z raised to minus 1 becomes Z. As Z raised to minus 2 is taken common, what leaves here is only 1. Similarly, what we do in the denominator is we are going to take Z raised to minus 1 common from each of the terms. So I'll take Z raised to minus 1 common from this term. We'll take Z raised to minus 1 common from this term as well as from this term. So overall we have taken Z raised to minus 1 3 times common from each of the term, which is making it as Z raised to minus 3. When we now take Z raised to minus 1 common, what is the modification in this factor? This factor becomes Z minus 1 by 2. The second factor becomes Z minus 2. And the third factor after taking Z raised to minus 1 common from it becomes Z minus 1. So this is how we have tried to take the terms common, all the negative powers common from each of the terms. Now what we have here is Z raised to minus 2 and Z raised to minus 3 in the denominator. So when we move this Z raised to minus 3 in the numerator, it is Z raised to plus 3, Z raised to Z with a power of plus 3 and Z with a power of minus 2. Overall, we get a power of Z to be plus Z with a positive power of plus 1. So the term after adjusting these two becomes Z in the numerator. This Z will multiply inside the numerator and we get now the numerator to be Z cube minus 2Z square plus Z, and the denominator is as shown. Now here, how will I apply the partial fraction? But what do I observe is, before I apply the partial fraction, do my given transfer function is satisfying the condition of a proper transfer function. Is it a proper transfer function? If we observe, the order of the highest order of the numerator is 3. Similarly, the highest order in the numerator is also 3. If I multiply and simplify this, the highest order will be 3. So numerator is with an order which is equal to the denominator order, and therefore we say this is not a proper transfer function. Always the numerator transfer function, numerator should have a power which is less than the denominator. And for that, what do we do is we'll take Z common from the numerator and put that Z on the left hand side term. So what leaves here is now Z square minus Z plus 1, which is a order less than the order of the denominator. We can now apply partial fraction to this. So if you see here, we have applied partial fraction to this particular term. Now we have three factors here. So we can have a upon z minus 1 by 2 plus b upon z minus 2 and c upon z minus 1. So we have three factors and therefore we get three terms. Now the task is to find those values a, b and c. So how do I find a, b and c? Let me first of all cross multiply the given equation. So we have cross multiplied the terms here and we get an equation as shown here. This helps us to identify by substitution of which z value, which of the coefficients becomes 0 and which is the only term which remains in the calculation. So if I now put z as 2, so when I put z as 2, I observe that this term becomes 0 and this term becomes 0. So it's only b that exists with z is equal to 2. And by substituting z is equal to 2, what value we get is, we get b value as 2. Similarly, if I now put z as 1, right, when I now put z as 1 here, what do I get is a term becomes 0 because there is a term z minus 1 here. This becomes 0, therefore a becomes 0. Similarly, b also becomes 0. The only term that I get after I substitute z as 1 is the c value. So my c becomes equal to minus 2. And similarly, when I now put z as minus 1 by 2, right, I have only a term existing. The b term becomes 0 because I have a term here z minus 1 by 2 and z minus 1 by 2 in c also. So when I put z as 1 by 2, these two terms gets cancelled, resulting in only the a value, which I get a to be 1. So this way, by substituting appropriate z values, we can cancel the remaining parameters, retaining only one parameter into the system. And this way we calculate the values of a, b and c. So putting the values of a, b and c back into the equation, we have a system equation as shown here. So this is a value, this is b value, and this is the c value that we have put into this equation, and we have obtained a new form of this equation as shown here. We know that this equation was nothing but x of z by z. Now we'll put this z back onto the right hand side. So we have z upon z minus 1 by 2. This term becomes 2z by z minus 2, whereas the third term becomes 2z upon z minus 1. Now further what we do is we take z common from the numerator and denominator so that we have the z transform equation back in the form of the terms where we are having z with negative powers. Right? So we have taken z common from the numerator and denominator, giving us the equation in the form as shown here. Similarly, we'll take z common from the numerator and denominator. Z gets cancelled. What we have in the denominator is 1 minus 2z inverse. Similarly, we'll take z common from numerator and denominator, leaving the denominator term as 1 minus z inverse. Now the thing is, we have, from this equation we have to come back to time domain. For this we need to closely look at what is the ROC of the given problem. So what is the ROC? Let us look back at what is the ROC. So the ROC for the given problem is z between 1 and 2. We have ROC for the given problem that z is between 1 and 2. So let us put that ROC condition in front of us before we decide what is the final time domain equation from the given Z transform. So if I look into the first equation, 1 upon 1 minus 2Z inverse, this is in a form which is obtained. If I look at the Z transform equation, this is obtained by taking the equation n is equal to 0 to infinity 1 by 2 raised to n z raised to minus n. If I have an equation which is of this form, then by applying the identity of Z transform, I get the equation as 1 upon 1 minus 1 by 2. Right? If I apply identity to this particular equation is obtained by an equivalent representation of it in the Z transform as 0 to infinity 1 by 2 raised to n z raised to minus n. This fits into an identity where it is equal to 1 upon 1 minus a, right, z raised to minus 1 here. This is very similar to the identity. And what is the identity? So I can even write the identity for you to understand. So identity is n is equal to 0 to infinity a raised to n is of the form 1 upon 1 minus a. Right? So this is very similar to the identity that we know. So this equation is obtained, or this form of Z transform is obtained actually The mathematics behind it is this. It means that now I identify that my signal xn is nothing but 1 by 2 raised to n, and therefore I write it to be 1 by 2 raised to n. Now, whether this is a right-handed signal or a left-handed signal is decided by the ROC. So what is the ROC? ROC is greater than 1. And what is the condition of ROC when I look at it here? So ROC should be greater than 1 by 2. Right? So here I understand that this particular pole, look at the pole value. The pole value is 1 by 2. So this pole value which I look at here is not lying in the ROC region, right? And therefore I say that my given signal is right-handed. My Z is greater than 1, whereas the pole value is half. So mod of Z greater than 1 indicates that the ROC is outside the circle with respect to the pole value 1 by 2. So with respect to the pole value 1 by 2, the ROC is outside the circle, and ROC outside the circle indicates that it is a right-handed signal, and therefore to confirm that it is a right-handed signal for this particular part of the Z transform, we attach the representation of UN. UN doesn't change the meaning or the magnitude of the given terms, but UN specifically indicates that the signal is completely right-handed. Similarly, look at the second part of the equation. What is the pole value here? The pole value is 2, right? We find the pole value to be 2. So if the pole value is 2, then looking at the ROC is mod of Z less than 2. So pole value should be less than 2, right? And the pole value is 2, whereas the ROC is less than 2. It means that this particular pole lies inside the ROC. So if it is lying inside the ROC lies inside with respect to this pole. ROC is inside the circle, right? Because the pole value is 2 here. So with respect to this condition, we understand that the ROC is inside the circle. So ROC inside the circle with a pole value of 2 indicates that the given signal is left-handed signal. So the moment we understand that this part is corresponding to a left-handed signal, how do we write the representation of it in the time domain? So representation of it is given by u of minus n minus 1. So this particular term, when we attach it into the system, we mean that it is a left-handed part. Whereas what is my xn here? If I compare it with the standard signal, right? If I compare it with this, my xn here is 2. So I have 2 raised to n u of minus n minus 1, and further the left-handed signal we have to consider a minus sign. So overall this part or this term of the given expression is a left-handed part. So left-handed signal we have attached with u of minus n minus 1, indicating that it is completely left-handed signal. What is my xn here? If I compare it with the standard equation, here my xn is 2. So it becomes 2 raised to n. And a minus sign is necessary when we go for anti-causal or a left-handed signal. So we need to have a minus sign. So this is about the second term. Moving to the third term, what is the pole value here? The pole value is 1. So this pole value, what is our ROC? ROC is greater than 1. It means that this pole doesn't lie in the ROC, or ROC is outside this pole. So ROC outside the pole indicates a right-handed part. So therefore, for the right-handed part, we again attach a UN to this particular term, indicating that this part is corresponding to an entirely right-handed signal. So we write U of n. What is my xn here? If I compare this signal with the standard signal, my xn is 1 here. So 1 raised to n is how I get the time domain representation of this part of the equation. So overall, how do I write my equation is 1 raised to n is nothing but 1. So this is the final time domain representation for the given signal. Moving to the next example. In the next example, we have been given a system equation, transfer function. There is no ROC specified here, and we have been asked to find the inverse Z transform. So what is the very first thing that we do? Looking at the previous problem, we first of all try to express the given expression with positive powers of z. So to get a positive power of z, we'll take the highest power of negative power common from the numerator and denominator. So the highest power of z here is minus 1. So what leaves inside is now z minus 1 by 3. Similarly, we'll take z inverse common from this particular term and z inverse common from the second term. So with z inverse common from the first term, I get z minus 1 here, and with z inverse common from this particular second term gives me z plus 2. Overall, z minus 1 into z minus 1 gives me z minus 2 in the denominator. I have already z raised to minus 1 in the numerator. So how do I finally write this? So I have z raised to minus 1 in the numerator and I have z raised to minus 2 in the denominator. So overall, I get this to be z, and that's why I have shown it as a z here. Now, with z in the numerator, right? What is the highest power we get from the numerator is 2. And what is the highest power when we simplify this is also 2. So the power of the numerator, and or you could say the order of the numerator is equal to order of the denominator. So we cannot apply partial fraction unless and until the numerator power is 1 less than the denominator. And therefore we arrange it as x of z by z. We reduce the power of the numerator by adjusting this z onto the left hand side. So what leaves now is z minus 1 by 3 by z minus 1 into z plus 2. We can now apply partial fraction because this is a proper transfer function. So applying the partial fraction, we can express this as a upon z minus 1 plus b upon z plus 2. Right? Cross multiplying this, we get the terms as shown. If we put z as minus 2, a term becomes 0. We get the b term. If we put z as 1, b term becomes 0 and we get the value of a. So with this, we have done the calculation as shown here. If we substitute z as minus 2, a term will become 0. And what is the value of b we get? It to be 7 by 9. If I put z as 1 here, if I put z as 1, b term becomes 0, only a term exists and we get the a value to be 2 by 9. If I put z as 1, I get a value to be 2 by 9. So substituting back a and b values into the equation, we have the equation as shown here. We'll adjust the z back onto the right hand side. We'll send the term z, which is on the left hand side, back onto the right hand side. So I have the term 2 by 9z by z minus 1 plus 7 by 9z by z plus 2. Right? We now bring back the equation into negative powers of z. So we have taken z common from the numerator and the denominator, which gives me denominator as 1 minus z inverse. Similarly, taking z common from the numerator and denominator gives me the equation in the form 1 plus 2z inverse in the denominator. We at this particular stage can apply the understanding of z transform and bring back or express this equation in time domain. Right, so I'll quickly once again revise you what is the basic identity that we use. The basic identity is always of the form n is equal to 0 to infinity a raised to n z raised to minus n. If this is the case, how do we write it? We write it as 0 to infinity a z raised to minus 1 with a common power n. Right? And now we can apply the identity and we get it to be 1 upon 1 minus a z inverse. If I apply the identity, I get it to be 1 upon 1 minus a z inverse. Right? So where your term a is nothing but your time domain signal xn. So look at this equation and look at this equation. So your xn is 1 here. Your xn is 1. So how do you write it? 2 by 9, 1 raised to n, un. Since they have not specified here any condition on ROC, we will consider that the given signal xn is completely right-handed. So without any ROC for the given problem, we'll assume that the given system is completely right-handed. So what is the evaluation of the first term? we get it to be 2 by 9, 1 raised to n, because my a term is 1 here. So 1 by is 1, 1 raised to n un. Similarly, at the second term, it is 7 by 9. What is my n here? My xn is 2, but I need a minus sign, and therefore I need to take it as minus 2 raised to n un. Why minus 2? Because for the identity we need to have a minus sign, but there is no minus sign here. For adjusting the minus sign, we need to change the sign of 2, and therefore it becomes minus 2 raised to n un. Considering that the given signals are right-handed, we'll attach the parameter un. So this is how we have obtained the time domain signal from the given Z transform. Moving to the third example. So here is a third example discussed. You have been given a transfer function and you have been asked to find the inverse Z transform using partial fraction expansion. Now how do I solve this particular problem? First of all, let us make the negative powers of z positive. So how do I make that? We make it by taking the highest negative power common. So what is the highest negative power? Z raised to minus 2. So I'll take z raised to minus 2 common from all the terms. So what leaves here is z square. 1.5 z inverse becomes 1.5 z. zero point 0.5 z raised to minus 2 becomes 0.5. So by taking z raised to minus 2 common, I have got an equation which is all with now a positive power of z. We will put the z raised to minus 2 in the numerator, so we get it to be z square. So z square upon z square minus 1.5z plus 0.5. With this, now we will try to find the factors of the denominator, because unless and until we have the factors, we cannot apply partial fraction expansion. So we need to find the factors of the given equation, right? So the factors that is observed for the given transfer function is z minus 1 and z minus 0.5. So if you multiply this, you get back your system equation. So with this, we have found the factors. So factor of the numerator is z minus 1. In the denominators are z minus 1 and z minus 0.5. We can now apply partial fraction expansion. So we have taken z on the left hand side, and what we get is a upon z minus 1 plus b upon z minus 5. Cross multiplying this and substituting z as 0.5, we get b value. Substituting z as 1, we get a value. So this way we have got the values of a and b. So a turns out to be 2 and b turns out to be minus 1. So expressing or substituting back this a and b values into the equation here. If we substitute a and b values into the equation, we get the equation in the form 2 upon z minus 1 minus 1 upon z minus 0.5. We can put this z on the right hand side back, so we get it to as 2z minus z, right? So this is how we have got the equation. To further apply or convert this into time domain, we'll first of all try to put it in negative powers of z. So taking z common from the numerator and denominator, taking z common from the numerator and denominator, we have the equation 2 upon 1 minus z inverse and 1 upon 1 minus 0.5 z inverse. Now we will evaluate this given system for 3 conditions on ROC. So we'll try to evaluate this given condition of the problem for 3 conditions on ROC. So let us first of all think about what will be the effect if we take ROC to be greater than 1. What will be the effect on the Z transform if we take ROC to be greater than 1. So what will be the effect on the time domain signal? Whether this part represents a right-handed part or a left-handed part, or this part is a right-handed part or a left-handed part, will be decided by what ROCs we take. So in the first case, if I take my ROC to be greater than 1, what is the pole here? The pole here is 1. Right? What is the pole here? The pole here is 0.5. So what do I observe? The pole for the first function is 1 and ROC is greater than 1. It means that ROC does not contain this pole, or ROC is outside the circle with respect to this pole, right? And therefore this part of the equation for the given condition indicates that this is a right-handed signal. Similarly, look at the second equation. Here my ROC is mod of z greater than 1. Here the pole value is 0.5. So ROC is outside the pole. So ROC being outside the pole indicates that it is a right-handed signal. So both are right-handed signals for the condition when mod of z is greater than 1. So if both are right-handed signals, we know that we need to attach an information which tells us that it is right-handed. And what is that information? That information is appending un. So when we append un to the given signal, we can confirmly say that it's a right-handed signal, right? So what is my xn signal here? It is 1. So 1 raised to n is nothing but 1, and therefore we write it as 2 into un. This 2 into un. Similarly, what is my xn here? My xn here is 0.5. So 0.5 raised to n un is the time domain representation of this particular equation in z domain. So finally, what is the time domain signal we get? So this part of the signal is now 2 raised to un, whereas this part of the signal is 0.5 raised to n un. Now let me move on to the next condition. If I put my ROC mod of z less than 0.5, if I now take the second condition, mod of z less than 0.5, let me look at my first pole, right? My first pole is at 1. So with respect to this pole, this ROC is inside the circle, is it not? The pole is at 1 and ROC is less than 0.5. So with respect to this pole, if we plot it in the z plane, then this pole, with respect to the position of this pole, the ROC is inside the circle, inside this pole 1. The ROC is of a circle of radius 0.5 and the pole is at 1. So with respect to this pole, we observe that ROC is inside, and if ROC is inside, then this part of the signal is a left-handed signal. So if this is a left-handed signal, then what is the information we need to append to confirmly say that it is a left-handed signal is appending u of minus n minus 1. Appending u of minus n minus 1 indicates that it is a left-handed signal. So with the analysis of ROC and the position of the pole, we understood that this part of the given Z transform equation is a left-handed signal, and therefore we have appended u of minus n minus 1. Whenever it is a left-handed signal, anti-causal signal, we need to additionally take a minus sign. So what is the overall equation? What is my xn here? Xn is 1. So 1 raised to n is nothing but 1. So what leaves me is minus 2. Minus is taken because it is an anti-causal signal. So minus 2 u of minus n minus 1 is the representation of this part of the equation. Analyzing the second half of the given equation for the ROC mod of z less than 0.5. What is the ROC here? What is the pole value here? The pole is zero point 0.5. The pole value is 0.5 and ROC is less than 0.5. It means that this, with respect to this pole, here my pole is 0.5 and here my ROC is less than 0.5. So it with respect to this pole, ROC is again inside. With respect to the position of this pole, where is the pole? 0.5. And what is ROC? ROC is less than 0.5. So with respect to this pole, the ROC is inside the pole, right? So ROC is a region inside with respect to the position of the pole, and therefore again this part of the equation is indicating that it is a left-handed signal. So if it is a left-handed signal, we need to attach u of minus n minus 1 along with a minus sign. So that minus sign is making this sign to be plus. And what is my xn here? My xn is 0.5. So what do we get? We get it to be 0.5 raised to n u of minus n minus 1. Why u of minus n minus 1? Because it is a left-handed signal with respect to this ROC condition. And whenever we take a left-handed signal, we need to take a minus sign, and that minus sign changes this sign, making it plus. So this is for the second case. Now let me analyze the third case. So what happens for the third case? For the third case, look at the pole value for the first part of the equation. So the pole value here is 1. So the pole is at 1. And where is the ROC? ROC is between zero point 0.5 to 1. ROC is between zero point 0.5 to 1. So with respect to this pole which is at 1, ROC is between zero point 0.5 to 1. So it means that ROC is inside with respect to the position of the pole. So if ROC is inside, it means that this part of the equation is representing a left-handed signal. So if this is a left-handed signal, when we express this in time domain, we need to attach u of minus n minus 1 to it, along with a minus sign. And what is my xn here? Xn is 1. So 1 raised to n becomes 1, and therefore we have not written 1 raised to n. So what is the thing that we get from the first part is minus 2 u of minus n minus 1, indicating that it is a left-handed part. Similarly, analyze the remaining half of the equation for respect to this ROC. What is the pole value here? The pole value is 0.5. And what is ROC? ROC is greater than 0.5, less than 1. But ROC is greater than 0.5. And what is the pole value here? It is 0.5. So with respect to the pole value, ROC is outside. Because pole value is at 0.5 and ROC is greater than zero point 0.5. So it means that for this part of the equation, the ROC is outside the circle, right? ROC is outside the circle, and therefore we need to consider that if ROC is outside the circle, it is a right-handed signal. So this part is representing a right-handed signal. So how do we emphasize the right-handed part? By incorporating the un term. So we have put un term indicating clearly that this is a right-handed part. And what is my xn here? Xn is 0.5. So it becomes 0.5 raised to n un. So this is the way, friends, you solve the problem on partial fraction expansion for finding the inverse Z transform.